I originally intended my previous video to be the last video on this section, but then there are still some lingering miscellaneous examples that I still want to show you. So in this video we're going to do three things. First of all, we're going to use these formulas to construct R20, so this will be the radial component for the wave function with n equal to 2 and L equal to 0. And then we're also going to construct R21. And then 3, we're going to talk about the degeneracy of the electron in the hydrogen atom. So we're going to do these three things in this video. So first of all, let's start with this. So let's try to derive R20. So I'm going to derive the overall form of R20, and I'm not going to normalize it yet. So one of the problems later on in this section will involve normalizing this function, so I'm going to leave normalization to that part. So here I'm only going to derive the general form of this, of R20. So in order to obtain R20, we start off with this formula. So we have 1 over R, and then we have y to the power of L plus 1. And remember, y can be expressed in such a way where a is the Bohr radius and n will be the n given over here. So in this case, our n is equal to 2, so that means our y is equal to r divided by 2 Bohr radius. And then we raise this to the power of L plus 1. L is equal to 0, so we just raise it to the power of 1. And then after this, we multiply it by this e term, so e to the power of negative r divided by 2a. And then we multiply this by v of y. And so in order to obtain v of y, we know that v of y is equal to this summation over here. So what we need to do is to find these constants. So we can find these constants by using this recursion formula. So we start off with some arbitrary value c0, and then we use the recursion formula to obtain c1, c2, c3, and so on until this chain of coefficients finally reaches 0, and then we can stop. So starting with c0, we can immediately obtain c1. So we can just directly apply the recursion formula. So we have 2 times j plus L plus 1. So in this case, j is equal to 0. And then we have plus L, L is equal to 0. And then we have plus 1. And then we have minus n. In this case, n is equal to 2. So we have minus 2. And then in the denominator, we have j plus 1. So j is equal to 0 in this case. So we have 0 plus 1. And then we also have a j plus 2L plus 2. So we have j, which is 0, plus 2L, which is also equal to 0 because L is equal to 0. And then we have plus 2. And so this is what we have. So in the denominator, it's going to be equal to 2. In the numerator, we have 1 minus 2, so this is negative 1 times 2, so we have negative 2 C0, so negative C0. So C1 is equal to negative C0. So using C0, we have defined C1 in terms of C0. So taking C1, we can now derive C2. So C2 is going to be equal to the value given by the recursion formula. So we have C1 multiplied by this expression here. So once again, we apply this formula. So we have 2 times j, in this case j is equal to 1, and then we have plus L plus 1, L is equal to 0, and then plus 1, and then minus n. In this case, n is equal to 2, so we have minus 2, and you can see that in the numerator, we already have 2 minus 2, so this is equal to 0. So we don't need to worry about the denominator because this whole term is going to be equal to 0. So you can see that the chain of coefficients stop after C1. So we have C0, C1, both of these are non-zero, and then the rest, C2, C3, and all the way to infinity, they're all 0. So what this implies is that v of y is going to be only composed of 2 terms. It's going to be equal to C0 plus C1y, and then the rest of the terms will all be equal to 0. And then we know that C1 is equal to negative C0, so we can just directly apply this, so we get something like this. So we have C0, 1 minus y. And so that leads us to the conclusion that R20, R is going to be equal to. So now we can just take this expression and then substitute the expression that we had for v of y directly into this expression here. So first of all, you can see that the r's, they cancel out, and then we have this constant c0, so I'm going to put this c0 up here, and then we have divided by 2a, and then we're going to have v of y, this y expression, and then instead of writing out as y, I'm going to write it as r divided by 2a. So we've included v of y, we've included these expressions, and then we also need to include the e to the power of negative r divided by 2a. So there you have it. This is the expression for R20. So the only thing that remains to be done is to find what this constant C0 is, because don't forget this is an arbitrary constant at this point, and then we can find this by normalizing this function. So I'm not going to do that in this video. All I'm going to do is to derive this general form, and then you can do the normalization if you're interested. So the next thing I'm going to do, so I've completed this goal. Next thing I'm going to do, I'm going to also show you how to do R21. So it's just another example to illustrate how we can apply these formulas over here. So we're going to do R21. So once again, we start off with this formula. So we have 1 over r, and then we have y, which is equal to r divided by 2a. And in this case, L is equal to 1. So we raise this to the power of 2 because it's L plus 1. And then we have e to the power of negative y, so e to the power of negative r divided by 2a, and then times v of y. And then once again, v of y is equal to this summation. And then in order to obtain the constants, we once again use the recursion formula. So we start off with a C0, and then we keep on obtaining subsequent coefficients. So for any arbitrary C0, we can see that C1 is equal to C0 multiplied by this expression, which is equal to 2, and then we have times j plus L plus 1, so j is equal to 0, L is equal to 1 for this case, and then plus 1, and then we have minus n, and in this case n is equal to 2, so minus 2. So once again you see that the numerator is already equal to 2 minus 2, so this whole thing is going to be, so we don't need to worry about the denominator, this whole thing is going to be equal to 0. So you can see that for the case of R21, the chain of coefficients immediately stop after the first term, so that only the first term survives. All the rest, they're all going to be equal to 0. So this implies that, so let's get this out of the way. So this implies that C1 is going to be equal to 0, and then C2 is going to be equal to 0, and all the rest is going to be equal to 0, so that means v of y is just going to be equal to C0, just a constant. And so now we can substitute everything into R21. So you can see that there's an r squared here, so we can cancel that out. So this becomes 4a squared, and then this is going to be C0. So in the end, you see that R21 is equal to C0 divided by 4a squared, and then times r times e to the power of negative r over 2a. So there we have it. This is your R21. And then once again, the only thing that remains to be done is to normalize this. And then once you normalize this function, you will find what C0 is. So now I've completed this second goal. So finally, we're going to talk about degeneracy. So what exactly is degeneracy? So degeneracy is refers to the number of different states that have the same energy. So recall that the energy level is only related to the quantum number n. And so you can see, remember that n can take on any number. So for any chosen number n, we also have a lot of freedom on what L could be. So L could be equal to 0, 1, 2, all the way to n minus 1. And then for any given number L, the quantum number m can be equal to 0, plus minus 1, plus minus 2, all the way to plus minus L. So here you can see that there are 2L plus 1 choices, and here you can see that there are n choices. So for any given number n, so let's say our n is equal to 8, and then for the choice n is equal to 8, you get a certain energy level, and you can see that you can have a number of different states that share the same energy level. So the degeneracy is going to be the exact number of different states that share the same energy level. So the degeneracy is going to be represented by this symbol because it's related to the quantum number n, and then we can find the number of different states that share the same energy level by considering the number of choices we have for L and M. So you can see that for any choice of L, you have 2L plus 1 choices for M, and then for any given number n, you have the value L can take on n different values from 0 to n minus 1. So we can just apply, in order to find the degeneracy, we can consider this expression. So L goes from 0 to n minus 1, and then for every different value of L, the number of choices you have for M is equal to 2L plus 1. So this summation will give us the total number of different combinations that lead to the same energy level. So all we have to do is to evaluate this expression. So we can see that we can break this up into two parts. We have 2 times the sum of L, where L goes from 0 to n minus 1, and then we have a summation of n terms where all the terms are just equal to 1. So here, evaluating this expression is actually just equal to 0 plus 1 plus 2 all the way to n minus 1. So we can use the formula n minus 1 times n divided by 2 for this expression. So we have n minus 1 times n divided by 2. And then here we're just adding 1 n number of times. So we start from 0 all the way to n minus 1. You have n choices. So we just plus n for this expression. So these cancel out. And so you see you get n squared minus n plus n, which is equal to n squared. So, and this is going to be the degeneracy for a energy level indexed by n. So if, let's say you're dealing with a case where n is equal to 8, you get a certain energy level, and then there will be a total 8 square states that will share the same energy level. And so this is how you can obtain the degeneracy for the electron in a hydrogen atom.